In this presentation, I want to discuss harmonygrams, a graphical notation system for three-voiced music which was specifically designed to facilitate the perception of harmonies. I will start out with some remarks about the motivation for this work and the context of it. Subsequently, I will show how the harmonygram concept can be derived as an extension to Andrew Killick's global notation for the special case of three-part music. And finally, I will present some application scenarios. Our work emerged as part of the research project Computational Ethnomusicology of Traditional Georgian Vocal Music (GVM), which was jointly hosted by Meinhard Müller at the University of Erlangen and myself at the University of Potsdam in Germany. For that reason, all my examples will come from traditional Georgian vocal music. One of the general questions which we pursued in the GVM project was how to deal with the representation, or in the terminology of this session, notation, of this originally oral tradition music in the times of multimedia recordings and web technology. This is not purely an academic question, as it is related to how this music is passed on to future generations and to people who are not exposed to the immersive mechanisms of learning this music through oral tradition. In 2016, Nanam Javanadze and myself spent the summer in the mountains of Georgia to collect the so-called GVM dataset, a collection of more than 200 multi-channel, multimedia recordings of traditional Georgian music and a fantastic dataset to explore all kinds of representation scenarios. Our most sophisticated approach was a web-based audio-video interface in which a cursor follows the pitch and note trajectories while displaying the actual chords, which will show up here, and the location of the individual notes on the overall pitch distribution. In addition, one can control the volume of the individual channels while watching the videos of the singers, listening to the music and reading the lyrics, which will appear here. To give you a brief impression of at least one dialect of traditional Georgian vocal music, I'm going to use this tool now to let you listen to the beginning of the song Elia Lirde from Svaneti in northwest Georgia. This kind of representation documents a performance in a pretty comprehensive and unbiased way and contains a lot of what one usually wants to capture in field recordings. However, since it requires very specific data, it does not correspond to the current standard notation practice in ethnomusicology. The standard practice still involves the transcription of audio signals into Western 5-line staff notation, and this causes various problems. Besides the well-known issue with the inappropriate Western tuning system, which for example can introduce artificial semitones into traditional Georgian music, Western notation also fails to do justice to the importance of the harmonic aspects of traditional Georgian vocal music, which are for example expressed in the way how singers interact harmonically. Traditional Georgian singers are well known for their remarkable ability to rapidly adjust their intonation, often to achieve pure harmonic intervals at particular locations in a song. This phenomenon, as you can see here from the date of origin of this citation, has already been noted by Siegfried Nadel nearly 100 years ago. Here you can see the results of a recent acoustic study of this phenomenon by Meinhard Müller and myself. Shown is the histogram of all notes in the so-called Erkomaishvili dataset, which were longer than 0.5 seconds and which showed clear signs of intonation adjustments. The intervals which are most often adjusted are the fifth, 700 cents, the octave, 1200 cents, unison, 0 cents, and the ninth, 1400 cents, maybe even the fourth with 500 cents, but not the third. Traditional Georgian singers seem to orient each other very much by harmonic coordination. Actually, not only on the short, but also on the longer time scales, which I may come back to at the end of my talk. The point I want to make with these remarks is that in order to understand traditional Georgian vocal music, it is important to not only focus on its melodic, but also on its harmonic content. For traditional Georgian singers, the perception of the harmonic content of a song, sometimes referred to as vertical thinking, is an intuitive and natural process, which is favored through the mechanisms of oral transmission through many years of practice and continuous exposure to the music. For singers who are used to learning songs from Western 5-line staff notation, rapidly recognizing chords can often be a major challenge. And this brings me to one of the main aspects of my talk. What we are looking at here is the transcription of a Georgian chant, which will be our example song for the following discussion. What do we actually see when we look at this score? That, of course, depends strongly on our experience in score reading. But even independent of our score reading skills, I believe that the first thing most of us perceive is melodic information. Even if we cannot read scores, we can recognize the rough melody contours from the ups and downs of the notes in the individual staffs. The determination of the exact pitches takes already some efforts, because we first have to identify the kind of clef of each system and the number and type of accidentals. But when it comes to decipher the harmonies, we have to think even harder, because we have to scan the score sequentially and determine the harmony for each harmonic state one by one. So, in terms of Daniel Kahnemann's model of human thinking, the recognition of melody contours from a score would, at least for experienced score readers, belong to the fast category, while the perception of harmonies would belong to the slow category. And that's a pity, because for singing practice as well as for music analysis, it would be very convenient to be able to access the harmonic information in a piece of music at the same speed and ease as the melodic information. And that's exactly what we try to solve with the harmonygram concept. So here's the idea. What you see here on the top panel is the beginning of the score of our example song. As I just outlined, for the perception of the absolute pitches, one has to learn and memorize the key signatures as well as the meaning of the accidentals. All of this is doable, of course. Many people have learned how to read scores. But on the other hand, if we visualize the individual melodies in Andrew Killick's global notation, in which notes are shown in an absolute time pitch frame by horizontal lines with a short vertical bar indicating the onset, the melody becomes much easier to perceive. But we are interested in the visualization of the harmonic information of the scores as well. And there's an incredibly simple solution for all three-voiced music. I forgot to say that I call this graph Melodigram because it essentially contains all the relevant information about the melodies contained in the score. So for the visualization of the harmonic information, we can simply use the vertical spaces between the melody trajectories, shown here, and color code them according to the corresponding harmonic intervals. With three concomitant voices, we perceive three harmonic intervals. From the top to bottom, these are interval 1 between the highest and the intermediate voice, interval 2 between the intermediate and the lowest voice, and finally interval 3 between the lowest and the highest voice. Let's start with interval 1 and 2. So here you see now a list of all the harmonic intervals in this song in all voice combinations. So we could do the color coding manually if we remember that 1200 cents are an octave, 100 cents is a semitone, and 200 cents a whole tone. So the first interval is 700 cents, which would make it a fifth, which corresponds to this sand color here. The second one is 200 cents, which corresponds to the gray color, and so forth. So when we let the computer do the painting, we obtain this nice colorful image. We can now play the same game for the third interval, the interval between the lowest and the highest voice. If we put the resulting plots side by side, we have the complete melodic and harmonic information. But the resulting two separate plots are still difficult to perceive. We cannot simply merge the two diagrams because the interval columns occupy the same regions in the time-pitch space. This, however, can be solved by shifting the interval columns in the right plot, the intervals between the lowest and the highest voice, to below the bass voice melody, so that they are still tied to the bass voice, but hanging below instead of standing above. Now we can merge the two plots into one. And we get a single plot, the harmonygram. Now all melodies and all harmonies are displayed in a single graph. Harmonygrams have really nice properties because they contain the complete melodic and harmonic information of a score, including the durations. There's no need to be able to read scores to understand a song. The chords can easily be recognized by their color code. Transposed chords can be immediately identified by their relative vertical positions, and chord progression patterns translate into image sequences which humans are very good at analyzing visually. Another nice property of harmonygrams as well as melodigrams is that they can easily be adapted to different tuning systems. This involves first the transformation of the actual note pitches into scale degree indices, the technical details of which are described in a recent paper in Musicologist, which then can be transformed into any heptatonic tuning system. For the example in the right panel, I've arbitrarily chosen the tuning system proposed by Zariatelli and Vesciapizze in 2014. During the remaining time of my talk, I will illustrate the potential of the harmonygram concept in three different analysis scenarios. As the first scenario, I want to discuss the use of harmonygrams in the context of structural analysis of chord progressions of individual songs. Here, for example, we are looking at the harmonygram of our complete example song. We can nicely recognize that this song, like most church songs, is organized in individual phrases. Each of the phrases ends with a middle and the bass voice. So the middle voice is the blue line and the bass voice is the black line going to unison. This happens here, here, here and here, while the top voice, the red line, goes to a fifth above it. So this situation shows up here, here, here and here. So this song is organized in 4 different phrases. If we now organize the phrases vertically, it becomes very easy to compare their internal structure. What I can immediately see, for example, is that all phrases start with identical chords of 2 stacked fifths. The first 3 phrases have very similar cadences, which is different from the final cadence. So these 2 are actually identical. The beats 14 to 34 and beats 70 to 90s are identical, as are the beats 5 to 9 and 66 to 70. So there's a lot of information which can be read of this graph immediately. As the next example for the use of harmonygrams for analysis, I want to mention their usefulness in the context of studying groups of similar songs. Because all the information is coded as visual patterns, it becomes very easy to study variations of similar chord progression sequences, like this one here, which are slightly different. This is something which Simcha Aram and myself have started to work on, trying to understand the chord syntax of Georgian polyphony. Yet another nice property of harmonygrams is that they can also be calculated directly from audio recordings. if one uses the pitch trajectories of the individual voices instead of the note trajectories from the scores. This is what I'll demonstrate in my last example. In the introduction, I've mentioned that Nana and myself spent the summer of 2016 in the mountains of Georgia to collect what is now called the GVM dataset. A particular gem in this corpus are recordings of funeral laments called Zer in the Swan language and Zari in Georgian. And here you see a map of their recording locations. And here you see the harmonygrams of all 11 Zer recordings in the GVM dataset. At the time of our study of Swan funeral dirges, we still used a different color scheme for the harmonic intervals, and the name harmonygram did not exist. So what is shown here is what we called harmonic melograph plots at that time. I want to point your attention to two aspects of this plot. First, all the pitch trajectories in most songs, here's a nice example, jointly undergo a very slow continuous pitch rise in the course of the dirge. You can see this here, here, and here very nicely. This can reach up to approximately 500 cents, a fourth, over 3 minutes. Second, it can be seen that the intervals between the bass and the top voice, which is indicated by the vertical bars hanging below the bass voice melody, are dominated by the bluish color. You can see this everywhere, which represents 700 cents, a fifth. In other words, most of the times bass and top voice move in parallel fifth, which is immediately recognizable from the harmonygrams. All 11 recordings belong to 5 different variants of Zer, and these are shown here in such a way that at the top we have short durations, small ambitus and fairly simple structures, which then changes to longer durations, larger ambitus and more complex structures at the bottom. In other words, from the top to bottom, the harmonygrams are aligned according to increasing elaboration of the acoustical structure. One of the questions which puzzled us was if the musical character of a Zer is related in a systematic way to any contextual aspect of the funeral ritual, for example, to the geographical location. Here you can see the recording locations and the locations of origin of the different Zer variants plotted on a geographic map. The region is very mountainous, as you can see in the overview in the upper left panel. Mount Elbrus, which you can see in the upper left, is the highest mountain in the whole Caucasus mountain range. The location of origin of the different Zers, shown by red circles, red discs, are all in or very close to the Nguri River Valley, which is shown here by the blue line. If we now line up the harmonygrams according to their locations of origin, we can see immediately that the ambitus, the duration, and the complexity of the harmonic and melodic structure of the Zer systematically change along the course of the river. And this is all immediately visible in the harmonygrams. Can you imagine trying to visualize this with scores? For the sake of completeness of the story, I want to briefly mention that my co-author Nanam Javanadze, who couldn't make it to Bologna, used the harmonygrams calculated from her transcriptions of the Zer for a complementary musicological analysis. And based on our joint analyses, we came to believe that the color Ushkuli variant, which is shown here in the upper right, can be seen as an embryonic model of the Zer's musical grammar, which is then developed downstream of the Nguri River to more sophisticated variants. All of this can be explained by the increased exposure of the downstream settlements to other musical dialects. This brings me to the end of my presentation. Since this is a conference on analysis, I didn't cover the use of harmonygrams in singing practice at all. However, I want to mention that a harmonygram-based song collection of several tenths of traditional songs has been made available, together with information regarding the use of harmonygrams in singing practice and some exercises through the GVM project website at the University of Potsdam. To wrap up, let me just leave you with a list of what I believe are the most important properties of harmonigrams for analysis of three-part music. Thank you very much for your attention.